Hello, Algebra 2 students. We are starting Unit 2, so it is all about transformations, which you did a whole bunch of last year in geometry. So sort of the same stuff, but we're going to talk about it within function notation, so it's going to look a little different. So you need your note packet, which you should have gotten after the test. And then if you have maybe like two different, a pen or pencil or highlight or something like that, it's probably going to be helpful for the notes for today. So the first thing we're talking about is translating or shifting functions. Oh, sorry guys, if you can hear Teddy barking in the background. It says, given the graph f of x, the function f of x plus k minus k is going to move it one way. And then if you have plus h or minus h on the inside, we'll move it a different direction. All right. So let's take a look at these and then we'll come back and fill in this. All right. So the graph that we're starting with, and actually let's draw it off to the side. There's not really a space, but we'll make a space. So f of x equals x squared is just a little parabola where the vertex is right on 0, 0. So it's going to look a little something like that. And if you did not have that vision in mind, you can type in x squared, and then you can just hit zoom 6, and I'll bring it up on mine so you can see it. There's that perfect little parabola. All right, so the goal is if we adjust the equation following all the directions, what happens? So with the first one, f of x plus 2. So if we just add 2 on the outside here, so I'm going to make it x squared and then plus 2 on the outside there, and we graph it, we get this guy right here. All right, so if you follow that vertex point is now up at 2. So you end up with this. All right, and do the best you can to sketch it there. All right, I'm going to switch this next one. This next one is f of x and then minus 1. So keep the x squared, and then out here, I'm going to change this to minus and then 1. So we go to graph that. Oops, did I not type it in? Oh, there we go. So blue is the original, red is this guy. So you can see that it's shifted down 1. All right, as for these ones, in case you're like, well, how am I supposed to do this? Think about what we did in the prior unit. If you were doing like f of 5, you'd put a 5 in for this. So if I'm going to do f of x minus 3, I need to plug in an x minus 3 right here. So into the calculator, you're going to put in the quantity x minus 3 squared like that. All right, so let's plug that guy in. So leave the original one, and then I'm going to put in parentheses x minus 3, close it up, and square it, just like that. So now when I graph it, there's the original. And now here is this guy. So if you take a look, the vertex is actually over here at positive 3. Last one, you know the drill. You're going to make it x plus 4, that quantity squared. So come on down, change this to a plus 4, and then hit graph. So here's the original one. And then there we go. All right, so left 1, 2, 3, 4. And you might have even guessed that, like, hey, if minus 3 made it move right, plus 4 is going to make it move to the left 4. All right, so I'm kind of following that vertex point around. Right? So let's kind of look at it as a summary. So as a summary, if I have a plus value on the end, it shifted it up. That's the first case right here. So this means it's going to shift the graph k units up. All right. If you have a minus 1, it shifted it down 1. So minus k means you're going to shift it down. So these two affect the graph vertically. So it's moving it up or down. As for the ones where it's inside, so x minus 3 or x plus 4, when it was minus, it shifted to the right. Oops, I can come back here and say down. So when you have x minus h, it's going to move to the graph to the right, whatever h units are. And then when you have plus 4, this one moved to the left. So when you have x plus h, this is going to go to the left here. So these are a horizontal translation. So vertical, up or down. Horizontal, we are going left or right. All right. So since it kind of helps to see it one time, now you can trust that, all right, those rules are going to work. We don't necessarily have to use the calculator unless you want to. All right. So with this first graph coming up here, it says graph f of x equals absolute value of x. Right? This is what we refer to as the parent function. Parent function is like the most basic of that type of graph. So absolute value, it's not shifted anywhere, nothing else is going on. It is just basic absolute value. So it's going to be that V shape. All right. So you can kind of picture what's happening there. All right. So when it says graph this guy, well, you can use your calculator. You could plug in a couple values, whatever works. If you think about like plugging in, like -2, absolute value would be 2. -1 would be 1. 0, 0. 1's 1. 2 is 2. Or you could go into y equals and do it that way. Otherwise, take a moment and just plot some of those points. And then if you have a straight edge around you, take advantage of it. I think I've got one sitting over here. So connect the dots, make it nice and pretty. All right. Now it's ask you, on the same set of axes, graph f of x minus 3 and then minus 2. So I want you to first think about what translation this is. So looking at the rules up top, if you have a minus on the inside, that means we're shifting to the right 3. And you can say shift or translate here. And then on the outside, if you have a -2, that means you're going to be shifting down 2. So right 3, down 2. All right. What you can do, could you use the graphing calculator here? Absolutely. Otherwise, take each of these points and you can just walk them from the location that they're starting at to the location where they're going to land. So what I mean by that, take the ones that we had plotted. So like maybe I start at the point -2, 2, and I can go right 3 and then down 2, and there's its new location. So here's where I'm going to use a different color just to make it easier. All right. And then take this next one, walk it to the right 1, 2, 3, down 2. I can take the vertex, walk it to the right 3 and down 2, and then keep on moving. Walk this guy right 3, down 2, and you should see that same graph being produced. It's just literally been slid over to the right 3 units, and then down 2 units. So it's almost like a little copy paste. Now, if I'd wanted to use my calculator, what would I type in? Well, I would just type in that g of x would be equal to the absolute value of x minus 3 like that, and then -2. That's what it would have looked like. Otherwise, I can label this as g of x. The blue for mine is the original f of x. All right. When it says describe the differences, all right, well, there's a lot of things you could say. I mean, it's literally in a different location. But I actually want to talk about the similarities and the differences. So I want to talk about what are the similarities, and then what are the differences. So let's start with the same stuff. Right? Hopefully you're seeing it still has the same shape. Right? So you might even notice like the slope of the lines there being the same. It has the same domain, which goes from -infinity to +infinity, right? Same end behavior. Because as x goes off to infinity, so does y. As x goes to -infinity, y goes off to +infinity. So same end behavior either way. Right? And when something has the same shape, you might even remember from geometry in the same orientation that it is referred to as an isometry. There's a little bonus vocab word right there. Right? But in terms of differences, well, obviously different locations. So along with those different locations means that you have different x and y intercepts. Different vertex, and the range changes. So, for the original f of x, the range there was all the y values greater than 0, or I should say greater than or equal to. And then for our g of x here, because the graph got shifted down, so did the range of values. So it was y greater than or equal to -2. So just some things to notice that, yeah, it's still the same shape. It has that same behavior, but when you move it to a new location, everything about it kind of changes along with it. When we flip on over to the next page, we are going to jump right over example 2, and we are going to move on to example 3. So under example 3, make sure you guys can see it okay here. Whoops, moved a little too far there. It's saying the function f of x is shown on the grid. The second function, g of x, is defined as f of x plus 2 minus 3. So now I love this example because with the first one we did, we could rely on the calculator to do the work for us. In this case, we don't have an equation to plug into the calculator. So it's really important that we understand how to move this without defaulting to the calculator doing the work for us. Right? So when you look at this funky little graph, it's kind of like a slanted line, we got a horizontal line, and then one last little piece. So it would definitely be like a piecewise function if we had to define, how did that get created? Otherwise, when the second function is saying g of x is equal to this right here, right, we can talk about how to get that. So when it says identify how the graph of f of x has been transformed to produce g of x and then sketch it, all right, well, go back to those rules on the first page. If we have a +2 inside the parentheses, that's code for it's going to shift or translate to the left 2 units, right? And then the -3 means that we're going down 3 units. So let's do that. So you can take each of these points. You could turn them into coordinate points if you wanted to, but I think these are fairly easy to just say, let's take the corners and go, all right, left 2 and down 1, 2, 3. Walk this corner, left 2 and down 3, and keep playing that game. Right, and what we should see is that same shape emerge, same size that it was before, and then connect all those dots. Now, if you don't have a straight edge, be as neat as you can be so that you don't end up with a big old mess on your paper. So that's the first part. The last part is asking you, what is the value of g of 1? So you're using your transformed graph now, and you're answering that question. So we're going over to x equals 1, and we want the point 1 comma what? So if we go over to 1, we're down 1, 2, 3, 4. So that would be -4 right here. For the sake of a little practice, what about if we said, what is g inverse of -2? Ooh, hopefully we haven't forgotten everything from the last unit. If we are asked for an inverse function, so remember, this would be the same as me saying, what is g of x? When is that equal to -2? So I want to think about that as a coordinate point of something comma -2. So go down to -2 and then go over. I think we could pretty confidently say that's our value. So -1, 2, 3, 4, 5. And there we go. All right. Let's try one more. This next one, let me slide up. You kind of have like a little zigzag. It sort of looks like the trending of like stocks or something crazy like that. So it's saying the graph of f of x is given. So this is our f of x. Woo, there we go. And it's saying the function g of x. All right, so sort of the same type of thing. We've seen it a couple times now. Is given by f of x plus 3 and then -1. So again, I want you to think, how is this thing going to translate? Right. So you can say shift or translate. That's up to you. +3 means we're going left 3. -1 means it's going down 1. So take a second and graph that. So walk each of those kind of corner points. So left 1, 2, 3, down 1. All right. And then connect the dots. All right. And then that is our g of x. Okay. When it says, what is the smallest solution to where f of x equals g of x? All right. If I want to know where they're equal, that is simply where they're intersecting, where they have the same y value. So if I ask like how many intersection points, take a look. The original one crosses the new function 2 times. So these 2 little spots right here. So there's 2 total, but it's asking you what's the smallest solution. So when I look at the 2 values, the smaller x value would be further to the left, right? So the smallest x value is furthest to the left. And now, depending on how accurate your graph looks, it may be easier to see it or not. If you look at mine here, mine's pretty accurate. If I go over, this is the one furthest to the left, and that would be at the point -2, 1, 2, 3. Now, depending on how the question's asked, if it says what's the intersection point, I would say -2, 3. Whoops, sorry guys, zoomed the wrong way there. But when it's saying, for what value will these be equal, it's really just asking about the x value. And so at x equals -2, those 2 functions will be equal to each other. Right? That can be tricky sometimes, knowing whether to give the x or the y. But because they're setting the y's equal already, you're just saying what x value that happens at. Right? We have one last page of notes to look at. So when you're ready, flip it on over to that next page. And here, these are going to go back and test a little bit about what we know in terms of domain and range. So this first one says, given the graph of the function f of x, so it's just this little line segment here on the grid, and the function g of x, which is defined as g of x equals f of x minus 2 and then minus 4. So really quick note to self, think this means we're going right 2, we're going down 4. All right. So when it says, what is the domain of g of x? Well, you can either calculate it by taking the domain of this one and shifting all the points right 2 and down 4, or we could graph it first. So since this is still new, let's sketch this guy first. Oops. Making up my own spellings here. All right. So we're going to go right 2 and down 1, 2, 3, 4. Take this guy, right 2, down 1, 2, 3, 4. And then let's connect the dots. So once you see it, it makes the question a little bit easier to answer. So in this case, we end up with the domain of g of x. So we're going left to right from -1 and then over to 1, 2, 3, 4, 5 is where it stops there. Excellent. All right. What's the range of g of x? So again, this was left to right. When we talk about range, we're talking about the bottom to the top. All right. So the lowest value, that's this guy right here. Bring it over. That is 1, 2, 3, 4, 5. So -5 and then up to -1. So we're seeing a lot of those same numbers, but make sure smallest to biggest here. Now, could we have just looked at f of x itself and then calculated? Yeah, right? Think about shifting to the right affects the domain. Shifting down affects the range. So what I mean by that, if I look at the domain of like the original f of x, just to kind of show it to you as an example, it starts at -1, 2, 3. And it goes over to +3. So it goes from -3 to +3. If I take each of those and shift them to the right 2, so think on a number line. If I shift this to the right 2, I'm essentially adding 2 to it. If I shift this right 2, I would add 2 as well. Well, -3 plus 2 is -1. 3 plus 2, that is 5. So I don't visually have to see it if I can understand how the shifts affect the domain and range. So anything right or left affects the domain. Anything up or down, that down 4 would affect the range. So I bring that up because this very next question has you evaluate without being able to see it. It's saying a function f of x has the domain from -3 to 10 in a range that y is less than or equal to 22. What are the domain and range of the function f of x plus 7 and then plus 10? All right, so two different things going on. We have a current domain from -3 to 10. The current range is it's all the values less than or equal to 22. Right? Think about what these transformations are doing. If I have plus 7, that means that you're going to move it to the left 7. If I have plus 10 out here, that means it's going to go up 10. Anything left or right, this is going to affect the domain. Oops, affect the domain. Anything up or down, that is going to affect the range. So think about how that affects it, right? So if on your number line, if you have all the values from -3 to 10 and we shift everything to the left 7, we're going to be subtracting 7 from each of those. So from this, I'm going to subtract 7. And from that, I'm going to subtract 7. So my new domain would be -10 and then up to 3. That should be my new domain. Play the same game with the range. If I take the graph and I shift every point up 10 units, that means I'm essentially going to take that graph, shift it up. I'm going to be adding 10 to the range. So if I add 10, my new range would be y is everything less than or equal to 32. So you have to kind of picture that you could see this graph in front of you, move it over, shift it up. Now what values does it fall between? So let's recap in class, all right? And then number 8, last one to look at together for right now. For number 8, saying given the quadratic function f of x equals x minus 4 squared and then minus 5, answer the following questions. How has the parent function y equals x squared been shifted to produce this guy? So they're just asking, how did we go from here to here? All right. So if I have x squared and then it goes to x minus 4 squared minus 5, what you want to think of is on the inside of the parentheses, we tacked in a -4 or minus 4, excuse me. And then on the outside, we have a minus 5. So in terms of like function notation, on the inside went a minus 4, on the outside went a minus 5. So this is going to shift it to the right 4. This is going to shift it down 5. Right? And it's a good rule of thumb to just follow PEMDAS and think inside the parentheses first, outside after. Right? So translating it right 4 and then down 5. All right, given the parent function y equals x squared has a turning point. And for whatever reason, I don't love that term. So vertex, a vertex at 0, 0. Where must the turning point or the vertex of the new function lie? Mm-hmm. Well, oh, I just realized that I called it f of x. That's okay. So if we take the point 0, 0 and we walk it through those translations, we go right 4, down 5, all right? You can literally graphically think if I go to the right 4 and then I come down 5, what's the coordinates of that point? Well, that's literally going to be the point 4, -5, right? That's going to be your new vertex. And we sort of saw that with that first little question that we did, kind of figuring out the rules. All right, last part. Which has a lower minimum value, the function f of x or the function g of x? All right. Well, minimum value is referencing the y value. So which is the one that goes like the lowest? So the f of x from up above was this x minus 4 squared minus 5. We already figured out that it's a parabola, and the vertex is at the point 4, -5. So if I think of it graphically, oops, it'd be over here, something like this. So without a calculator, oops, a little off the page there, you can kind of get a visual on what's happening. All right, for this one, think of the original function, the most basic absolute value. Its vertex point is also at 0, 0. So when I see -6, -10, that means the vertex is going to have been shifted to the right 6, and then down 10. So if I try to mentally sketch this guy out, it'd be over here at 6, and then somewhere down here at negative 10. And so instead of it looking like this, it would be down here. So which one has the lower minimum value? Well, look at the bottom of the graph. This one goes as low as negative 5. That one goes as low as negative 10. At this point, you should know the answer to the question, right? So make sure, answer that on the post video question. Which function has the lower minimum value? Is it the quadratic one or the absolute value one? All right. Talk to you guys tomorrow in class about it.